Yeah.
Okay, this is great. Perfect. Okay, thank you very much, Rachel. Last time I did a presentation on Zoom, I never managed to get the full screen. Okay, so you can see that I picked a bit of a challenging title because really I wanted to give you an idea of how, in a way, quite crazy it is to want to use a synchrotron to do safe health imaging. So what I will do in my presentation is an intro. I didn't know who the audience would be, so I thought I'll do an intro on the synchrotron radiation and IMBL briefly. And then in the middle, these four, from user program to patient outcomes, I've actually put in the presentation that I was asked to do a couple of months ago to the UNSTO board, who have been extremely supportive and impressed by the Breast CT program. And at the end, I wanted to give you an idea of how complex the safety system that we had to develop are. Current status, I will have to do it only in words because I ran out of time to add some slides and photos. But without further ado, let's have a look at the first part, synchrotron radiation in the IMBL. So the reason why I call it a death ray, this is a typical high power beam that you can get on a high power synchrotron beamline, such as the IMBL. Typically, you could have anything up to 30 kilowatt of X-rays. Of course, there's many components in the beamline that reduce this, but a beam like you see here, which is actually ionizing the air because it's so powerful, will set certainly a piece of wood on fire in a couple of seconds. So this is the reason we have to cool our optics. In terms of dose, we have done experiments on the IMBL with up to 50,000 grays per second. And typically when we do radiotherapy, we use a beam of 1,000 gray per second. So this is to be contrasted with our breast scans at the moment, where we aim at 2 milligray in a full scan of mean glandular dose. And in the case of radiotherapy, we go down to 1 to 3 grays in a irradiation. So you can see the challenge in getting this down to do safe breast scan. So what does it look like on the ground? That kind of big water tank-like building on the right is the Australian synchrotron building. And then the building on the left is the IMBL satellite building, where we will be doing the clinical imaging at the end of the tunnel, which bring the synchrotron to the satellite building. In terms of synchrotron light, let's see if it runs. This illustrates how the Australian synchrotron works. You have up to 2022, we had 9 beamlines. So we have a system of accelerators which basically fill the storage ring, and then the storage ring emits synchrotron 24/7. Well, not quite 24/7, 24 hours a day, yes, but we have 1 or 2 days stop every week. In terms of accelerators, we have a 750 MeV accelerator linear to produce the first beam, into a storage ring of 3 GeV, into a booster ring where they're taken to 3 GeV, and then transferred to the storage ring until there is 200 milliamps in there. And then the nice thing is that we operate in something top up, which means that the beam stays constant in intensity during the experiment. The main storage ring is basically not a circle, of course, it's a 28-sided polygon. And as I mentioned earlier, up to this year, we had 9 beamline. Now, quickly, how do we generate, why is synchrotron radiation generated? Basically, when you accelerate an electron, in this case, we force them to stay in a relative circle with a magnetic field. They receive an acceleration from the magnetic field, and that makes them emit radiation in a very narrow cone. And you can see here that on the IMBL at 35 meters, the cone typically is 12 millimeters, and at 135 meters at the end of the beamline, it's 46 millimeters. In order to get a wider beam, we actually use something called a wiggler, illustrated on the right, where we use an array of magnets in order to boost the energy up, boost the intensity up, and spread the beam sideways. One thing I want to mention here is that the 46 millimeters and 35 meters, the natural cone of radiation, this is the full width. It's Gaussian, so in practice, it will typically give us a size usable of about 25 millimeters maximum in the vertical plane. And typically on the IMBL, because of the wiggler and the 3.8 milliradian opening in the beamline, we can get a beam up to 50 centimeters. Now, what we use in terms of wiggler on the IMBL is a superconducting multipole device, 1.5 meter long, 31 period, 48 millimeters, cool at liquid helium temperature, so we can get to 4.17 Tesla. When we do the work for Breast City, we run the wiggler at 3 Tesla. And then, as I said, 3.8 milliradian into the beamline. Before I go on to the next section, I just would like to mention that we have a new $95 million BRIGHT program, which has been funded by all the partners, many universities and organizations, which mean that we are bringing up another group of beamline. 6 are funded. You can see them listed on the right. And the microcomputed tomography has already taken beam and will take its first users in the third part of the schedule for this year. And the next will be the biological small angle scattering beamline called BioSAX. Right, now let's go close and back to Breast City. So this is now, I will change the templates. Thank you very much for all those of you that sent comments and produced this wonderful impact template, which I've used for everything except the talk that I gave to the board. I kept this wonderful layout, as you will see, because all the slides were actually handed over to professional slide makers, and I didn't want to spoil that. So this presentation was to show how we go from a user facility with its programs, user program, to patient outcomes through collaboration and development over many years. And of course, this was written for the ANSTO board, therefore we emphasize ANSTO partnership and all the wonderful things we do at ANSTO, which will lead to the breast cancer diagnostic. So the main overview was how, if you have developed a capability, and in this case, the synchrotron was added to ANSTO some years ago. So you add the synchrotron capability to the palette of facilities at ANSTO. ANSTO is funded to benefit to all Australians, of course, through a lot of medical application. And in this particular case, we focus on the imaging and medical beamline as a key strategic investment for ANSTO and NHMRC in this case as well, as you will see. Then we partnered with all of you, really, with Patrick, with Sarah, with Tim, the key players from different universities to raise the funds in order to put together a project. And of course, this project have to fit within our government's priority on health. So this is the big picture. Behind this, of course, as you all know, the goal is not just to have a new tool on the synchrotron in Clayton, but is to see whether we could translate these wonderful new techniques to use it on emerging technology of compact X-ray sources, as if we can, this would then be able to be exported in hospital. So now, you know the challenges in breast imaging more than I do, since it is at the heart of your research program. But as you know, breast cancer is the most common cancer in women, and it is detected by imaging. And imaging at the moment for breast has got its failing and its disadvantages. We know about the low sensitivity in some types of the imaging. We know that it can lead to excessive radiation dose to this very radiation sensitive breast tissue. The quality of imaging is often insufficient, especially in the case of high-risk subject and high tissue density. So especially in younger women where the tissues are high density, it is difficult to get very good images who give the information we are after. Painful compression, this is the standard in standard mammogram, although there are techniques on the market, such as the dedicated CT, breast CT equipment. This is coming on the market where compression is no longer required, but they still fail on the quality of the image given. And of course, 60 to 80% variation in screening result, depending on quality of the image and who is looking at these images. So the goals of that project were better risk model, reduce the number of false positive, and reduce the impact on the subject. And of course, if we can do this, there'll be less cancer and we can reduce costs. So having a look, what is the magic, if we can say, of using synchrotron light to develop a new technique for breast CT? Well, the magic or the technique is a phase contrast principle. It is illustrated beautifully on the left. As you can see, one of those, I can't remember what they are called, those buoys or whatever that float on water. So what you see here is the surface of a swimming pool, receiving direct light from the sun. If you look at the surface of the pool, believe me, it's completely flat, you can see nothing. You would not really see the ripples by eye. But when the sunlight is refracted, in all the tiny little features on the surface of the pool, or a big feature such as the buoy there, then what happens is projected several meters away at the bottom of the pool, and you get this amazing structure, which is the phase contrast principle, which means that you go from something that doesn't seem to have any features to something that shows a lot of features. This is illustrated in the middle image there, which is a chest X-ray of a rabbit, which is done within phase contrast. And although you can see the ribs and you can see the mass of the lungs, you can't see much of the detail in the lungs. Whereas if you extract the phase contrast from the image using fancy algorithm, you can see that we can see all the individual alveoli, which means that the air pockets, air fluid, and very low density tissues can all be differentiated in the extraction of the phase and the image. And that is the beauty behind our project. So having a little bit look at the timeline of the project and of the IMBL. The IMBL had its first experiment in 2008 in December. And then in 2013, we completed the extension of the IMBL to 140 meters and had imaging in the satellite building. In 2017, we started to do mastectomy imaging with our partners. Many of them are watching this presentation now. Tim, Patrick, and the extended team. In 2022, this year, we have completed the change in infrastructure for the IMBL to do breast cancer tomography. And we basically are now ready to do clinical scans, but the safety system has yet finished to be tested. 2022, yeah, I haven't modified my slide, I missed that one, was the validation with volunteer patient. Unfortunately, this will be pushed into the first half of 2023, mostly because of the serious limitation we have had in the last 2 years. Not just COVID delaying various programs, but not enough resources available at the synchrotron because of the new Beamline program. So 2023, I should say, to 2026, well, actually 22-26 is correct, is the extension and translation of clinical phase contrast imaging with our new impact grant. So we step back and having a look at what happens from 2008. The experiment were done in the main building, okay? Original Beamline, minimum optics experiment in the main building. And that phase was funded by the Victoria government. And we were just one of the initial 9 Beamline in the synchrotron. By 13, things changed a lot. The Victoria government gave us extra to a total of 11.5 million. And then the NHMRC gave us 13.2. This led to an extended infrastructure and being able to image in a new building, 3-story building at 140 meters. Then we were able to equip, still with the 13.2 million of an HMRC funding, which we got in 2009, we were able to equip the Beamline, not with the bed that came later. You can see the bed sitting on the robot, but this $1.5 million robot to position the patient and to do the CT scan using the rotation stage on the robot was added, if I remember right, in the early period of 2016. And that, I think, let's see if it runs. Yes, you can see a rotation about the breast position of the bed. We have tested rotation up to 30 degrees per second, and that is what we are at the moment. All right, now came the big players and came the extra funding. I must, ANSTO decided to support extensively the breast CT program once it was funded through grant from an HMRC, with Patrick being the lead on this grant application, and put 4.3 million of infrastructure funding to re-equip the IMBL ready for breast CT. So from March 2017, which is when the project was funded, to now, about 5 years, we have implemented everything we need in order to do the clinical scans. Breast CT to be the focus of our clinical imaging program. I've said that, and that was, I think, the first grant that Patrick obtained from an HMRC, and the list of partners are in the third column on the right. So if I can just say a couple of things, key partners in there, well, everybody is a key partner, but certainly on the clinical side, or certainly on the imaging side, I would say CSIRO on the processing of all the images. Monash Health is key to support so far to have supplied the tissues for the mastectomy development work. Monash has supplied a lot of know-how, especially in phase contrast. Our colleagues at Electrosynchrotron in Trieste have been critical in laying the foundation stone for breast imaging in 5, when they started to do the first tissue images. And of course, the NHMRC and ANSTO through the Australian government. So here are some images that were selected. You can see typically the way we do the CT is rotation about the breast. We take thousands of images, and then if we extract some of the slices from the stack of the images, we can of the 3D stacks, we can extract 2D images to compare them. And you can see an image on the left, which is a conventional CT slice, and an image in the middle there, which is a phase contrast CT slide. And I know that, you know, you could say the difference when it's seen on the screen might not be enormous, but in fact it is. When you look at the details, there is a lot of features which are not seen or badly seen without the phase contrast. One of the beautiful things of phase contrast is you can you use low dose. Basically what you do, you extract the information from a very noisy image, and the image is very noisy because we are not giving a very heavy dose to collect the data. Typically, to give you an idea, the dose ratio between non-in vivo work that we do on the Beamline and this kind of work on breast, it's 3 to 4 orders of magnitude, which is how we go to a very dangerous ray to a safe ray for doing clinical imaging. Now, lovely little diagrams on the right here is that you can actually tweak, or you can improve at least the image quality by tweaking the phase contrast. And that is one of the power of the technique. So looking, pardon me, the kind of overview of what has come out of probably about now 5 years of doing mastectomy tissues is that we have been able to develop the way that we do low radiation dose images on the Beamline. We have extracted the image quality by working with CSIRO. We have perfected the way we can reconstruct the images in 3D and do all the tiling. It gives us a better diagnostic accuracy, although of late I've been told, the jury is not out. There is still some tweaking to be done. And of course, as mentioned before, we have no breast compression since the breast is hanging kind of freely from the bed, from the position, the patient in a prone position. We have done to date more than 120 mastectomy tissues, which have been used to develop all the different techniques from data collection to data processing. So looking at the key, underlying driver of that synergy grant, the impact grant, is we would like, with this 5 million grant over 5 years, led by the University of Sydney, to do several things. The step one, which actually will go through the 5 years, is to optimize the imaging condition as much as we can and keep improving. But when we say establish a clinic, it means to go from a few cohort of patients to demonstrate that the technique is working and is worth using, to many more cohorts in order to demonstrate even more clearly and improve all the different steps from the data collection to the data analysis. We would also like to extend this to lung cancer diagnosis. Lung imaging is probably one of the leading activities on the IMBL. All the work has been done on rabbit kittens so far with the world expert from the Hudson Institute associated with the University of Monash. And they want to now extend from rabbit kittens, now that we have an expanded beam, to newborn lamb. And this will be a critical phase in improving the imaging and getting more relevant images, or more relevant in translation to human. So we would want to see, or to put together all these leaders in the field of lung cancer who have now joined the IMPACT program, to see whether we can use the IMBL to do lung imaging, in particular lung cancer diagnosis. The next and very, very vital step is to see whether we can, using compact X-ray sources, which are typically the size of a room, put phase contrast or get enough phase contrast out of one of these sources to basically develop a package which would be synchrotron light from a compact source and phase contrast imaging. And this package could then become a commercial entity which hospital could add within their precinct. Typically, a system like this would not be the size of the MCG as a synchrotron, but would be roughly fit into, say, half the size of the Monash Heart Hospital, half the footprint, the Monash Heart Hospital, which is being built on the other side of Blackburn Road from the synchrotron. So, as you know very well, members of IMPACT, the goal is to revolutionize breast and lung cancer diagnosis to reduce cancer mortality and morbidity. So I can see that I'm at 30 minutes, so I've got plenty of time. Now, I will go to my last slide for the board presentation. I think it is important to say who the key players have been. And of course, there has been all the team from the IMBL and ANSTO on the left, with Andrew Peel being a key player, since he's on the grant as, for the time being, is our director, although he will be moving on, I'm told, in about a year and be replaced as director of the synchrotron. In the collaborators, top of the list here, we have Patrick and Sarah, who have really giving us the drive from the imaging side. And you can read all the other names. You don't need me for this. And I, again, would like to mention Electra Synchrotron team, because we did learn a lot, extremely useful knowledge from them, from the 10, 20 years that they have been doing breast imaging, which I wouldn't say it enabled us to hit the ground running, but it did mean we could basically get on the ground without tripping at the beginning. On the clinical team, the same, you see the key people who have been involved here with us doing the mastectomy tissues so far. And I'd like to single out Jane Fox. Without Jane, we wouldn't be able to get tissues straight from the surgery onto the beamline and then back to the hospital for pathology. And of course, a special thanks to the individual who have consented to having their mastectomy tissues used for this research project. And at this stage, I think I will go to my last section, which is to give you a feel, a flavor for how do we achieve patient safety. And as I say, current status, I run out of time, but how do we achieve patient safety when we start with a beam that can literally set things on fire, but instead being able to have at the end the beam we want to get the data we want safely out of a human, live human person, and make sure that nothing can go wrong. Well, behind this, we spent typically nearly 2.5 years developing the safety side and writing a large pile of documents which went to our PANSA, our radiation regulator, to eventually lead to us being allowed to image volunteers. So, as you know, the research volunteers will be imaged in our bunker, 3B, the concrete enclosure. The imaging protocol means that there's a bed attached to the robot, and then the patient lays prone on the bed, and we rotate at the appropriate speed, where the speed is defined by the comfort of the patient and the dose rate of the X-ray beam and the number of images that we want to collect to have a CT scan. The robot that we use is known as the Patient Positioning System, PPS. This is a $1.5 million device which came fully certified, developed by a company in Germany who uses KUKA robots, and are the only company that are licensed to move humans with such robots at the moment. So we had to modify the IMBL extensively in order to add a lot of safety cover in my next slide. And behind this, we had to develop a safety system, which is called the Imaging Patient Safety System. And when I say develop, it means we had to do the design, we had to design the hardware. A PLC, programmable logic controller team, had 2 or 3 engineers working on this for many months. And then we added a new clinical mode to the personal safety system on the beamline. The personal safety system of a beamline is what makes sure that nobody can receive any radiation at all. It basically works on the assumption that nobody will be in a radiation room with X-rays on. Well, what we want to do with patient imaging, of course, exactly the opposite. We want to do imaging of someone in the room. So there has to be an IPAS, the Imaging Patient Safety System, integrated with the PSS to make sure that this can happen safely. And believe me, this is not trivial. And every time you make changes to something such as the PSS, in the case of the IMBL, it takes 3 days to revalidate the safety system. So we had to add a lot of new programs and features to the PSS, and they had to be added to the PPS so that we could integrate the robot safety with the radiation safety and the patient safety. So let's have a look at what happened to the beamline. So this is the layout of the beamline. Pardon me. With the wiggler on the right, this kind of rectangular array there. Various components are in the beamline, and I will not go through all of them. I will just describe the ones that are key for clinical. So once we have produced a monochromatic beam using a monochromator here, this is a 2 crystal from the monochromator. So typically at this stage there, we produce 30 kilowatt of X-rays. By the time we come out of a couple of components, a mask and some filters in the front end, we've taken this to about 3 kilowatts. By the time we go through a bank of filters, we only end up with less than 1 kilowatts. And then by the time we select wavelengths and reflect this single monochromatic beam 25 millimeter higher than the pink beam, we're talking much less than a watt of X-rays. So you could say it's not a very efficient system in terms of producing a lot of X-rays, but this is what we have to do in order to make the beamline safe. The first key component we designed and added is known as the clinical mode pink beam stop. This is a large block of tungsten with a small slot inside that is just the size of the beam we want to use for breast CT. And when it is lowered mechanically by hand into position, it is locked with a fortress key, which is the highest level of key system you can purchase. And that key, once it is removed, make it impossible for the block to move. It basically means that deadly, and I mean death ray, the pink death ray, cannot go anywhere outside this first enclosure. It is stopped not only by that normal block here, the photon stop, but by the clinical mode pink beam stop. That key, once I have removed it from the lock, is the key that is put in a special key exchange panel. And then when that key exchange panel is switched on using that fortress key, the key stays trapped. So there is no way we can start and proceed towards imaging patient and go and touch that block because the key has been removed and secured into a key cache. The next components which are critical, we have a new fast shutter, a fast valve, and test filters. So briefly, I don't want to go into too many details, but the fast valve is a valve that can stop the monochromatic mode in less than 20 milliseconds. The new fast shutter is a backup shutter which closes in about 5 milliseconds. The test filters are special filters which are used to change the intensity of the beam when we check that the IPAS is working correctly. It means when we are set up to image a patient, I can activate filters which can increase the beam by 10% or decrease the beam flux by 10% and verify that the IPAS pick up that change and close all the shutters immediately. So this is a component which is used to modify the X-ray flux and check that the safety system is working. The 4 new ionization chambers all monitor the X-ray beam, and they work in cross pairs so that we have redundancy. And they are the one that give a constant signal to the IPAS and say everything is well. If this signal changes, right, by more than 5%, then the IPAS will shut down the beamline. And the new imaging shutter is the shutter that opens when the patient has reached the scan velocity. So we basically accelerate the patient. When we reach the scan velocity, we start to collect, we open the shutter and start to collect images. When we have our images, we close the shutter and stop reading the detector. Then we have installed here a beam expander, which is a fancy set of 2 crystals, extremely stable, but they need some very careful tweaking to do the job. What they do is that the beam coming in is typically about 5 millimeters high, and the beam coming out is then 50 millimeters high. And then this beam continues to expand and linearly until it reaches the bunker and 140 meters. And when it reaches there, it is 8 centimeters high. And because of the slit, 28 centimeters wide, which we shut down, we close down to 23 centimeters. Now, when we achieve this, we have put on the side, not shown here, there are the last set of slits which set the size for the imaging of the patient to exactly the size of the new detector. And before those slits, there are 4 chips, very fast detectors, which monitor the beam coming down the beamline. And the reason why we have these new fast beam detectors is that they were developed at the University of Wollongong. So they have picosecond response time. Basically, what happens in the case of the iPass, if for something that we cannot really figure out how it could happen, but that's the way you design safety system. If when iPass thinks or knows that all the safety shutters, all the shutters are closed, these detectors detect any photons at all in the imaging bunker. They give, through the iPass, a direct order to the storage ring to kill the radio frequency cavities. And that means, of course, all the beamlines lose their X-rays because the whole storage ring goes down, but that can happen in 20 milliseconds. So this is the last resort. So basically we have 4 levels of safety in terms of how many shutters we can close, but this is the very last one. If everything went terribly wrong, we still would rely on this to close the beam. So let's have a look a little bit. So quickly, what did we change to enclosure number 3? We added, and this is really important, a new access booth. This access booth enables the radiographer to go in and out of the imaging bunker without having to touch the lead doors that we normally use, which weigh about a ton each and are very awkward. And the idea of this is that once we have transformed the 3B bunker into a safe imaging room, a different room search system is implemented. So the radiographer doesn't have to do what we normally do, press a lot of buttons and there's alarms and flashing lights. For the radiographer, this is just an imaging room. The radiographer has complete control of the patient, the robot, and the scan. So this is a very important change. And this is one of the reasons why we had to go through the safety system in detail to explain this to our Pansa in order to get the authorization. Now, the new detector here, and I don't have an image of it in that presentation, is a 1.5 million Dectris detector that was made in Switzerland, and it has 135 millimeters by 80 and a frame acquisition rate of 200 hertz. And this is important because if we can run at 200 hertz and we tweak the beam intensity or dose rate at the right value, then we could collect this, say, 2,000 images in 10 seconds, which is well below the breast hold for a patient. So that is the concept of the scan modification to 3B. Now, behind the safety system, these are the key things that we had to consider. We looked at the science requirements, which was what was a dose and a number of images which were required with a live patient to do it safely. We developed the experimental sequence. We did a risk assessment. This is a 32-page Excel spreadsheet, which is very complex. It took more than a year to develop it with about a team of mechanical engineer and safety engineer. And that all led to the BCT safety system requirement, the iPass. Now, the key thing, and I could show you many more slides like this. I'm sorry, I normally hate showing slides if you can't read the text, but I just wanted to illustrate that basically the way the procedure is made safe is there are 3 phases. There's a beamline staff phase, there's a medical physicist phase, and then there is a radiographer phase. The beamline staff phase is us with a lead that is clearly identified for preparation that will prepare the beamline for the imaging. And the way this is done is that, say, if it was me, my first step would be to go to the first enclosure, put the clinical mode ping beam stop in position and remove that key. Make sure all the rooms are closed on the way down the beamline, and then go to the satellite building, put that key into the key cache, and then turn it. And this will free a new key, which is the beamline staff key, which will remain in the pocket of the lead scientist preparing the beamline until the beamline is ready. And the there are three flow diagrams, such as the one you see here. The one you see here is phase 2, which is the medical physicist phase. And there is another one after, which is much shorter for the radiographer. And there is one before that, which is similar for the Beamline staff. But by the time the clinical person responsible for the imaging has decided how many images they want to collect, what is the total mean glandular dose they want to give, we set the Beamline to do that scan. When it is set up, we actually put a phantom into the bed, and we perform a scan like if the patient was there and measure the integrated dose. Once we have done this, we fill in a handover sheet for the medical physicist where we say we've done all this, we have got that dose, and we put our key in the key cache, turn it, free the medical physicist key, give the medical physicist their key. If they are happy with the report and the dose, they will activate their part of the flow chart and go through all those points. Before, when they're ready, the medical physicist will have verified everything, and then they will be ready to hand over to the radiographer. When they hand over to the radiographer, this is also done through the key cache. Then the radiographer basically has an imaging instrument and a patient, and they will take care of having the volunteer lie on the bed, move the bed to the scan position, tweak maybe in height and Y. There are guide lasers indicating exactly where the beam will be. And once the patient is ready, there will be an audio contact, constant audio contact, audio and visual contact between the radiographer and the patient. The radiographer will exit the room, close the booth, do a last check with the patient that they are happy, comfortable, and ready to go. When they are, they will say, okay, please hold your breath now. And they will just press the scan button. The scan will be performed in something like under 20 seconds. And then the radiographer will enter the room and the patient will be returned to the offloading position, or he or she will help the patient to move over to image the second breast. So this is give you a level of the complexity of the process. Believe me, when we are ready to do, nobody will see those charts. They will no longer need to be implemented. I would say we would have done all the work. And let's see what my last slide. Oh, see. So what I wanted to quickly show you there is the sequence, the safety sequence behind the work. So the way the response time of the iPass is made up of bits D1 through to D5. They basically, the response time that are associated is every motion. For example, if I take the shutter here, well, this shutter does close in 5 milliseconds, but there is a communication which is required. You have to look at the beam, analyze, decide what you do, send the signal, get the response time, send the signal to the next component, you have a response time. And so it goes, so that even if you have components that can move in 5 milliseconds, or the beam can be killed in a machine in under 5 milliseconds, it's in fact microsecond, the iPass needs processing time. And it has a response time of about 50 milliseconds. Therefore, the total time from detecting a fault or a wrong event and the final end of beam is 200 milliseconds, 0.2 second. So if you think that we're doing a scan typically, say, of 20 seconds at that dose rate, you can see that we have a very safe system. So thank you very much. As I said, I would have liked to add a few more slides showing you where we are today. So what I would like just to tell you that we have equipped the bunker with curtains. We are now looking into the best audio system to add. We are preparing, we still have, we received, in fact, yesterday, the last, the final controller for the PPS, which the radiographer will use with the graphic user interface for the radiographer. It's not implemented yet on the Beamline because our main engineer at the moment is on leave. When Navid comes back, this interface will be added. We will revalidate everything, and then we will be in a position to do various clinical scan in the radiographer way. At the moment, we do them and they're quite clunky, but then they will become smooth within a few weeks. Then we will start to plan the next set of tests with volunteers on the bed without X-rays. We do comfort tests not only for the rotation, but also for the new design that we have for the breast holder or stabilizer. Beside this, we are about to refurbish the outside lobby, the lobby outside the imaging room, with some very nice furniture that we'll have. We're buying from a First Nation registers suppliers, so they will be all Aboriginal design on the printout and on the furniture. What else? And I think probably most importantly, I think it's a good way to finish my presentation. Because Navid was away, that's the engineer on PLC, for a couple of weeks. He went back to Iran to see his family. It freed 3 days of the time that was allocated for Navid for us on the IMBL, and we decided to practice the full clinical process. It was the first time that we would put the Beamline, take the Beamline in a normal experiment mode, transform him and move it to the clinical mode, put in the dosimetry equipment. We have a phantom, which we made in-house, which simulate the density of a breast. We have a pharma chamber down the middle. So once we're ready, we do exactly what I said before. We do a patient scan, and we measure the integrated dose. Well, I have the pleasure to be able to announce that in the 2 setup that we did, Wednesday last week and Tuesday this week, so that means starting from scratch, putting all the components, putting the expander in, tweaking, making everything ready. It takes about an hour to make the Beamline ready. And we had a 2% difference in integrated dose between the 2 scans, which were conducted 1 week apart. So that was for us a major milestone, and it augurs well for the pre-operational testing that we have to start in October to get all the safety data we need to send to our PANSA to get the permission to image patient. And that's the end of my presentation. Thank you.
Thank you. Thank you, Daniel. Well, really, if we wanted to devise a more appropriate talk at the start of this series of talks around this project, I don't think we could have chosen a better one. I think that was just very, very good. It positions us beautifully for the talks that will follow over the year. So it really was an excellent explanation for the synchrotron. I think every undergraduate physics, radiography student would benefit.
I think we can better those slides. Slide quality benchmark's very high now, Daniel. Downhill from here.
It was, and it's the other thing that's obviously very important. It was very reassuring to see the emphasis that's going on patient safety. Now, I know that quite a few of us have to go in the next couple of minutes for other meetings, but has anyone got, I propose that if anyone has any questions, please maybe pass them to Madeline, and we could get a sort of a community of questions going on and a discussion. But has anyone got a quick question for Daniel? I have quite a few, but I'm gonna talk to you about those later, Daniel. Okay. So if there are no questions, is there anything in the chat? No. If there are no questions, then I suggest we call it a day there. And once again, thank you, Daniel, for a really tremendous talk that has, I think, for all of us that are not that familiar with the synchrotron, we now are a lot more familiar. So thank you.
Yeah. Sorry. Just one thing.
Sure.
I'm aware that basically more than 10 people is outside the impact team attend this presentation seminar. Thank you very much. So you are most welcome. Send your contact detail to me. So then I will send the invitation for all future seminar to all those non-impact team. Yeah.
Yeah. Thank you, Madeline. Good idea. All right. Well, thank you all, and we'll see you in a month.
Thank you.
Yeah.
Thank
Thank you very much.
Bye.
Thank
Thank you for
you.
inviting me. Thank you. Bye.
Thank you.
Well done, Daniel.
Thank you.